All right, hey everybody, it's Miss Manili, and I'm going to give you your last AP Stat lesson of the year on inference for linear regression. Everybody in my 2B class, say hey! All right. Okay, we're going to start with a quick warm-up that reviews our linear regression procedures that we learned way back in the beginning of the year. All right, so you want to make sure that you enter all of your TV hours in list 1, your GPA data in list 2. Yep. The whole time. All right, so once your data is entered, and first of all, let's talk about what this problem represents. It says we have a random sample of 10 high school students who produce the following results for the number of the number of hours of television watched per week and their GPA. So we're ultimately trying to determine if there's a relationship between how much TV you watch and your GPA. We might expect that if you're spending more time watching TV than doing your schoolwork, that your GPA might suffer, and so we might expect a negative association. So you're given a scatter plot, but if you forget how to construct the scatter plot, once your data is entered in list 1 and list 2, if you go to second y equals, you can set up your scatter plot. You want to make sure you turn it on. The very first graph is your scatter plot, and then you want to make sure that you're pulling your x and y lists from the appropriate list. So I've got them in list 1 and list 2. Now right now my calculator is in alpha mode, so if I want to do a zoom 9 and actually see the scatter plot, and that's what I've got. I also have an equation graphed. All right, so in my case, I've got a bunch of equations that I need to delete. Otherwise, they're going to conflict with my scatter plot. All right, so there we go. So when you're asked to describe the association, remember when it's two variables, okay, our scatter plot, we have to talk about the form, the strength, and the direction. The strength and direction are probably pretty obvious, but what do we mean by form? Is it linear? Okay, so when looking at the scatter plot, let's first of all label the axes. What does the x-axis represent? TV hours. And what about the y-axis? GPA. Okay, so how would you describe the strength, the form, and the direction using the context of the problem? Because on the AP exam, everything you write needs to be in the context of the problem. So who can tell me what they would write here? Can I get a volunteer? You don't have to speak into the microphone. Go ahead, Casey. You want to? Yeah. Just talk really loud. Okay. Yeah, put it in the context of the problem. There's a negative association between TV hours and GPA. Okay. Do you have more to that? Okay. A moderate, you want to throw linear in there somewhere? So maybe a moderately, that should be a y, sorry, moderately linear. It is pretty subjective, but there is a value that we can look at that will help us make it a little bit more objective. What is it? What did you say? R squared and what else? R. R in and of itself, our correlation coefficient, describes the strength and direction and gives us a more objective figure. When you're just looking at the scatter plot, it is relatively subjective. Okay, so there's a negative association between TV hours and GPA. You could also say that in general, the more TV watched, the lower the GPA. All right. So the next thing we're asked to do, guys, with me? The next thing we're asked to do is to determine the least squares regression line. Anytime it's referring to least squares regression, it's always talking about linear regression. Okay, so least squares means linear. So if we go to our stat calc menu, now the one thing I do want to just point out is your calculator has two linear regression commands. There's the command that's used option 4, and notice that in this command it's ax plus b, where the variable a represents your slope and b represents your y-intercept. If you scroll down a little bit further, there's another command for linear regression, but it's in a different form, where a is actually your y-intercept and b is your slope. I don't want you to get too hung up in the A and the B, but I do want you to recognize that in all of our inference techniques, we're referring to A as our y-intercept and B as our slope. So if you're using the first command, I don't want you to get the a's and the b's confused. So just remember, your slope is always going to be your coefficient of x. And if you just kind of keep that in mind, then it shouldn't matter if it's called a or b or m. It doesn't matter. Okay? So either of those commands will give you the correct equation. Just make sure you tell the calculator where the data is. We're not using a frequency list, so we can leave that blank. We do want to make sure that the calculator stores the regression equation in y equals. So to get there, we go to vars, y vars, and then click function, and then you can store your regression equation in any of those. I'm going to go ahead and do it in y1, and then calculate. Okay, and so remember, when you're writing your regression equation, it's just from sample data. It's an estimate, so we put a little hat on the y. And that would be equal to, in this case, A is our y-intercept. So it's going to be 3.823 plus our slope. Actually, it's a minus, isn't it? Minus 0.065 times x. Is that what everybody got? Okay. Now, if you don't have r and r squared on your calculator, you have to go to your catalog. So you're going to go to second catalog and then scroll down until it says diagnostics on, and then turn them on. Okay. So you're asked to interpret the slope and the y-intercept in the context of the problem. So let's talk about the slope. What does this negative 0.065 mean in the context of the problem? Okay, for every hour of TV watched in a week, GPA. Now, we want to be careful when we're describing the slope and the y-intercept from a regression equation, because this isn't necessarily going to be what happens for everybody. It's not necessarily what's always happening. So we want to make sure that we're describing like an estimate or an approximation. So we could say the GPA is estimated to decrease 0.065 points. Okay, so you do want to make sure that you're using the estimated or approximately or on average, that you're not describing it as being an exact value that's going to happen for everybody. And then what about the y-intercept? Our y-intercept is 3.823. What does that represent? Yeah, so this would be the estimated GPA of a student watching 0 hours of TV. Okay, and again, this is just an estimated or an overall average. And sometimes you'll find that your y-intercept doesn't make any sense in a problem. So for example, let's say this was like 15 something. Can anybody explain why sometimes the y-intercept doesn't make any sense for a problem? Exactly. So when our y-intercept is really located far away from all of our data points, sometimes, because we're looking at a line that extends forever, sometimes where it crosses the y-axis really is unreasonable considering where the rest of our data is. And there's a term that we use for that. Anytime you're making a prediction that goes beyond the data, extrapolation. An outlier is a point on the graph that is outside the rest of the pattern. But when we're making a prediction that's beyond our data, that's what we call extrapolation. Okay. The next thing you're asked to do is to state the values of r and r squared and then describe what they mean. So in this case, r is negative 0.814. And so r, what does that tell us? The correlation coefficient describes what? The strength and direction, which is pretty much what we were describing in that very first sentence. This tells us that there's going to be a moderately strong or moderate negative association. You want to be careful about saying that it represents a linear relationship without looking at the scatter plot. Because if all you're doing is looking at a value of r and you don't actually see the plot itself, you really can't say whether or not it's linear. So r alone just describes the strength and direction. Does anybody remember how to interpret r squared? Let me give somebody else a shot. Grace? Okay, close. So R squared in this case is 0.662, which basically is telling us that 66.2%, now it's not of the data, we're saying of the variation in the y variable. Because remember, when we looked, if I go back to my graph for a second, and now I see my regression line cutting through the points. It doesn't hit every point. So R squared describes the scatter of y values that are around the graph. So 60% of that scatter, 66% of the variation in the y variable, which in this case is GPA, is explained by or accounted for the regression equation. And we want to make sure we refer back to our explanatory variable on TV hours. Okay? The next thing you're asked to do is to construct a residual plot. You've got the steps to do that on your paper. I didn't feel like squeezing them in here. But for all of the inference techniques that you're going to be doing, every single problem is going to require a scatter plot of the original data of x versus y, a residual plot of x versus your residuals, and it's also going to require, and this is a new one, a normal probability plot of the residuals. So every single problem regarding inference on regression is going to require those three graphs. So let's review how to come up with the residual plot. It does take a few steps. So just to remember what a residual is. The residual is that difference or the distance between our point and our line. So the residual is basically, I can't draw on my smartboard over here, but it's basically the distance between every point and the line, that vertical distance. Okay, so a residual plot is essentially just going to turn this graph sideways so that my regression equation is a horizontal line, and we can focus on the scatter of points about that line. It makes a little bit more sense if you're dealing with a curve, because the residual plot will straighten out the curve, and then you can really examine the scatter. I didn't mean to do that. Okay, so we're going to go back into our lists if you haven't done this already. What we need to do is put our predicted values in list 3. So a residual is always going to be your observed y value minus the predicted. And so to get the predicted, I have to insert my equation. So I'm going to go to vars, y vars. I'm going to pick the function where I've stored my regression equation, and then I'm just using function notation. So instead of saying f of x, I'm going to use y1, and all of my x's are listed in list 1. And so this command is basically going to evaluate the equation for every single value of x that's listed in list 1. And I can see if I compare the values in list 2 and list 3, the values are pretty close. To come up with the residual, though, I actually want to subtract my actual minus the observed, which is going to be list 2 minus list 3. I said actual minus observed. Observed minus predicted is what I meant to say. So a residual is observed, which is also the actual data, minus what we would predict from our equation. And so you'll notice that some of those values are positive and some of them are negative because you have points above and points below the line. What do you think would happen if I added them all up? They should equal 0. They should cancel each other out. Okay, so to do a residual plot, we're going to go back into our scatter plot menu. We're still going to keep the original scatter plot, but we're going to change the y list to list 4, because now I'm just going to examine all my x's and all those distances. And if I hit zoom 9, I'll see a different pattern, or I'll see a different scatter plot, where this horizontal line is now my regression equation. And so we're just sketching. So it looks like I have a point here, and we're just going to sketch what we see. Doesn't have to be perfect. But in terms of interpreting a residual plot, what are the things that we look for, or what are the things that we don't want to see? We don't want to see any patterns, because a pattern would indicate that a linear model is not appropriate. So what looks good in a scatter plot? I mean, in a residual plot? Random. We want to have a random scatter of points. We want to make sure there's an even distribution above the regression equation as well as below. If there's any clusters, if there's any points that are significantly further away from the rest of the points, then that's not a good sign. So tell me about this graph. Is it okay? Is it a good representation? So something like this, where we know that there's an even scatter of points around the line, tells us that the linear model is appropriate. So the even scatter of points, that shouldn't be a comma, tells us a linear model is appropriate. Okay. And so knowing that the linear model is appropriate now lets me go ahead and I can make predictions. So in letter E it says to use your regression equation to estimate the GPA of a student who watches 15 hours of television per week. So the way I can do that, there's several ways that we can calculate it. Essentially I'm plugging in the 15 for X. Since I already have my function in Y1, I can again use function notation in my home screen and just evaluate Y1 at 15. And that'll give me a GPA of 2.85. Are we confident in that? Why? How come we're confident in that? Yeah, the 15 hours of television per week is within our data range. And if you compare that GPA to what we have in our table, it seems to fit pretty reasonably. But what about in letter F? If I do the same command but change 15 hours to 30, I get a prediction, but how reliable is it? Why is it not reliable? Yes, it's an extrapolation. Exactly. 30 is too far beyond our data to be confident. We don't have any data to support our model after, what is it, 24 hours, I think was the biggest number? Okay. All right, any questions about the warm-up? Okay. Okay. So we're going to start talking about inference for regression. We're only going to be looking at inference for the slope of a linear regression equation. There are other types of inference for regression procedures, but we're only going to be looking at slope. And we're looking at the rate of change between two quantitative variables. So we're going to be looking at confidence intervals for slope as well as tests of significance for slope to see if there's an association between quantitative variables. So those are our objectives for today. There are a lot more symbols that we're going to be using since our equations are different. We're not talking about a mean or a standard deviation or a proportion. We're dealing with slope and y-intercept. All right, so introduction. When a scatter plot shows a linear relationship, and this time we're talking about quantitative data again. Remember with chi-squared, we were looking at relationships between quantitative variables, categorical variables. Now we're moving back to quantitative. So we can use the least squares regression line fitted to the data to predict a y for any given value of x. If our data come from a random sample, then we also can make inferences about the population. And so some of the questions that we try to answer would be like, is there really a linear relationship between x and y in the population? Or could the pattern that we see in the scatter plot plausibly happen by chance? And another question that we might try to answer is, in the population, how much will the predicted value of y change for each increase of 1 unit in x? That's the slope. So we're going to be making some inferences about the slope. We're going to be estimating the rate of change for population and also testing claims. All right, the regression model. You guys are familiar with our y hat is equal to a plus bx. So just remember, in all of these notes, b is referring to our slope. So don't get the a and the b confused. So the slope b and intercept a of a least squares regression line, those are considered statistics because we calculate the regression equation from data from a sample. And so if we were to take a different sample, obviously we'd get a different regression equation. And so if we want to do formal inference, then we need to know a little bit more about the unknown parameters that A and B are estimating. And the parameters appear in what we often call a model of the process that produces our data. All right, some assumptions. And these are just kind of like what we have to kind of go in assuming is true. So if we have n observations on an explanatory variable x and a response variable y, so we're looking at n now represents the number of ordered pairs instead of, so n equals the number of ordered pairs, because we're going to have an explanatory and a response. So n is corresponding to the number of ordered pairs. And our goal is basically to study or predict the behavior of y for any given value of x. And so there are a couple of assumptions that we're going to assume going in, and that is that the response is going to vary according to a normal distribution, and that repeated responses are independent of each other. We're also going to assume that the mean response, so for any x, I'm going to get a different response, but the mean response for y is going to be in a straight line relationship. So notice that this equation here looks a little bit different than the equation on the previous page. And that's because the equation that we have here is for the population. So remember how we use Greek symbols to represent population parameters and then regular letters to represent our sample? Notice that we're using alpha and beta here to represent the y-intercept and slope of the population. They are not the same as the alpha and beta that we were referring to with the type 1 error and the power. Okay, so they're different. We're just using those as our variables for slope and y-intercept. So in general, I'm going to do a little table here. So we have our slope, we have our y-intercept, we have our sample, and we have our population. The slope in our sample we're going to call b, lowercase b, just a regular plain old b. And our y-intercept from our sample we're just going to call plain old a. But in the population, we're going to refer to the slope as beta and the y-intercept of alpha. And so those are the things that we're trying to estimate. Our equations are going to look a little bit different too. The actual linear regression equations that we come up with are always going to be of the form where y hat is equal to a plus bx. Let me fix that. But in terms of our population, we're looking at the mean response of y. So I'm looking at mu of y is going to equal whatever the population y-intercept is plus whatever the population slope times x. Okay, so this is the equation that we're going to be working with. This is the equation that we're trying to estimate. Okay, and that's just notation. So beta and alpha are unknown parameters because they're describing the population. And the standard deviation, so here we're describing the mean of y, the mean response. The standard deviation is going to be unknown, but we're going to assume that it would be the same for each value of x. All right. All right, so conditions for the regression inference. This is more along the lines of what we were saying before. The mean value of the response is going to follow our true, this is our true population regression line, which we're never going to know unless we do a census. And that all the values of the response variable follow a normal distribution. So this is basically what it would look like. Every time I take a sample, right? So if I have a sample, think about the GPA problem that we had with all the kids that were watching TV. So I take a sample of 10 students and I think, okay, well, if you're watching on average 10 hours, I'm going to have a couple students that say, yeah, I watch TV for 10 hours. I'm going to get their GPAs and I'm going to take an average. That average, if I take a different sample, is going to vary. So it'll be the same number of hours, but the mean GPA is going to vary. That variance is going to be a normal distribution. If I have a group of students and I'm looking at kids that maybe watch 12 hours of TV, I'm going to have a bunch of different GPAs that correspond with 12 hours. So each of my Ys, each of my responses now are going to follow a normal distribution. And that's what this graphic is basically representing. Okay. When we're looking at inference, when we're taking our linear regression equation, the slope we get is considered an unbiased estimator of the true slope. The same is true for our y-intercept. It's an unbiased estimator, and that is ensuring that we have a simple random sample of data. If there's any kind of bias in my data gathering techniques, then that's not going to be true. So you do want to make sure you're dealing with a simple random sample. The standard error about the line, and this is something that I don't think you actually have to use this formula. I believe it is on your formula sheet for the AP exam. But when you're doing the tests on the calculator, it'll calculate the standard error for you. A lot of times you're going to be given the output from like a Minitab program, and so it'll actually tell you what the standard error is. So I don't think you actually have to know that formula. But because we're dealing with mean and standard deviation again, we're dealing with a normal or a t-distribution. And since we don't know the standard deviation of the population, we're always going to be using a t-distribution. But notice this time the way our degrees of freedom are defined. It's n minus 2, and that's because we're dealing with two variables. So we're dealing with a t-distribution, but our degrees of freedom are now defined as n minus 2. Okay. All right. So when we're doing inference for regression, there are 5 total conditions. And so it's important that we think about each of them in the process. For example, the straight enough condition. This is pretty obvious. If I'm going to be doing regression about a linear equation, I want to make sure my data is linear. If I do a scatter plot and I see a curve, is it going to make sense to do a straight line regression? No. So if it's curved and I'm doing linear regression, I'm going to stop. There's no sense in going any further. So that's the first condition. The data obviously has to look approximately linear. It doesn't necessarily have to be a strong association, but it has to be an association that isn't clearly nonlinear. So if there's a definite curve, you're done. Independence and randomization, again, because we're dealing with different data points, you want to make sure, and so this condition is the same as it's been. Independence and randomization. Also, when sampling without replacement, you want to make sure your population is at least 10 times the sample size. So these 3 conditions are the conditions that we've been seeing the whole time. The other 2, so this straight enough condition you're going to show in your scatter plot. The third one, or the fourth one, has to do with equal variance. And this is making sure that the y values are spread evenly over your regression equation, and this is what you're going to show in a residual plot. So that's the second graph. And then this is the one that's new. It's the normality assumption, but we're looking at the residuals. So all of the residuals, which we saved in list 4, you're going to do a normal probability plot on your residuals. So each one of your inferences, you have the same 3 conditions that we've always had. The independence, randomization, and your population has to be at least 10n. The 3 that are new are your plots. You're going to have a scatter plot. You're going to be able to look at your scatter plot and say, yeah, the data looks pretty normal. It looks straight enough. You're going to do a residual plot and show that the points are evenly scattered about the line. That's our equal variance. And then you're going to do a normal probability plot on your residuals and show that it's normal. And then those are the other 3. Okay, confidence intervals. We're going to start here. All of our confidence intervals follow the same pattern where we take our estimate plus or minus our critical value, and our critical value is determined by our confidence level, and then we multiply by the standard deviation or the standard error. All confidence intervals have that same pattern. So the B here is referring to the slope. So you're going to take the slope of your regression equation. You're going to determine your critical value t, depending on what your degrees of freedom are and the confidence level. And then the standard error of your slope is this formula, which again, you're not going to have to actually plug anything in, I don't think. If you have data, your calculator will figure that out for you. And the other alternative would be that you're given a computer output that has the value on it. Again, since we're dealing with a t-distribution, we have degrees of freedom, and the way they are calculated is n minus 2 because we have 2 variables. All right, so let's take a look at an example. So this is one where you're given some computer output. We've seen this output before, but we didn't know what half of those numbers represented. So it says many people believe that students learn better if they sit closer to the front of the classroom. Does sitting closer cause higher achievement, or do better students simply choose to sit in the front? So to investigate, a statistics teacher assigned 30 students to seat locations in his classroom for a particular chapter and recorded the test score for each student at the end of the chapter. The explanatory variable in this experiment would be the row to which the student was assigned, where row 1 is in the front. So it says that this is an experiment. What are the words I'm looking for? What are the foundations for a good experiment? What needs to be true? Random assignment. Does it say anything about randomly in here? No. So without random assignment, can we make inferences about causation? No. So what is the first assumption we're going to have to make? We're going to have to assume that they were randomly assigned, even though it doesn't say it in the problem. What else is important in an experiment? Control. Do we have any control here? Not really, right? There's nothing to control against. And then what else? Replication. Do we have replication? Yeah, we have 30 students, so that's okay. And the last one, no, population, has to do with we have to have comparison. So we have to have something to compare to. And so is there any comparison here? It is a way of controlling. Yeah, they kind of go together. But it's not like I sat them, I have their current test scores and then I move them to see if it changes, or if, I'm not comparing their scores to anything. I'd probably want to change their seats and see if there's a difference between the seating arrangements. So this is not a very well-designed experiment, but nonetheless, we're going to continue. So let's take a look at the information that you're provided. We have only looked at, not even the S. The only numbers that we've looked at are the numbers in that first column and then the R squared. Those are the only things that we've looked at. Marshall, you still with me? Okay. And so both of these numbers that we have listed under coefficient provide us with the sample slope and y-intercept. The question is which is which? Does anybody remember which is which? Say that again? The slope is the bottom one. The one that is next to constant, if you think about it, your y-intercept is the constant. The row, that's our x variable. So the number that's next to that would be the coefficient of x. So this is our slope. And so if I wanted to write the regression equation, I'm going to say that y hat, don't forget to put a hat on it, is going to be equal to 85.706 minus 1.1171 times x. But now, if you take a look at those other columns, I know we ignored them at the beginning of the year, but do those terms now look familiar? What does SE of the coefficient stand for? Standard error, T. It's our T value. Now, and this P, what do you think this is? This is the P value, the probability of our sample. And so the T and the P go together. This is not the T that we're going to use in our confidence interval. It's the T that would correspond to our slope and y-intercept if we were doing a hypothesis test, which we'll do. Okay? So let's take a look at some of the questions. So it says to write the equation of the least squares regression line and interpret the slope. So we said it was 85.706 minus, actually I have this written down somewhere. Okay, so how would you interpret the slope of this line? It is. Use it in context. That's not what the slope represents. For every row you move back. Your score. Now be careful about the next part, because remember it's just estimated or it's an approximate. Your score is estimated. And we'll assume that's in points maybe. Okay, so remember when you're interpreting the slope, it says x increases by 1, the y value is either increasing or decreasing by the value of the slope. And then you want to make sure that you actually are using the correct variables in the problem and making sure you're using the context. So in part B, it says to identify the standard error of the slope. So which of those standard errors represents that of the slope? The second one. So 0.9472. Okay, and the standard error, it's similar to the standard deviation. It's basically describing, or we can basically expect the rate of change, because that's what slope is. We can expect the rate of change to vary about 0.9472 points per row in repeated sampling. Do I need to write that out? Does anybody need me to write that out? So we can expect the rate of change in the decrease in score by row to vary 0.9472 points in repeated sampling. Okay. Now in letter C, it says to assume the conditions for inference are met. Remember, there's 5 of them when we're doing linear regression. It says to calculate the 95% confidence interval for the true slope B. So in our formula, it says we're going to do B plus or minus T star times the standard the standard error of B. Well, what was the slope? Plus or minus. Now remember, the T that's listed in the table or listed in the output is not the T that we would use for the confidence interval. So how would we figure out the critical T value for our confidence interval? What information do we need to know? The degrees of freedom and the confidence level, right. So we know the confidence level is 95%. Now if I was using a normal distribution, I would just use 1.96 for my Z value, but I can't do that with T. So if I'm dealing with a middle 95%, I'm going to end up having to use the inverse T distribution, and I have to think about the area to the left. And so what area would that be? 0.025. Okay, and then we also need to know the degrees of freedom. And how many students were there? 30, and so we're going to do 30 minus 2, which gives us 28 as our degrees of freedom. So now we can go into the inverse T distribution. And so that's option 4, and I've got it in there already. And so the value we get for T is going to be negative 2.048. But remember, when you're putting it into the formula, you want to make sure you take the absolute value of that. And then what about the standard error? That's given to us, right? So 0.9472. So when we're calculating the interval, we want to do the subtraction first. So we'll do the negative 1. And that'll give us our lower bound, so it's a negative 3.06. And then if I just hit second enter and change the subtraction to a positive, to a plus, that'll give me the upper bound. All right. And so that gives me a positive 0.823. So tell me what you mean by not significant. Because we're not doing a significance test, we're looking at a confidence interval. What are you saying? It's 0.823. Yeah, sorry, that's just a decimal value. So notice that our interval goes from negative 3 to positive 0.8. What does it include? It includes 0. So remember, if we're talking about a slope and a rate of change, what does it mean if the slope is 0? Then there's no change. So since 0 is contained in this interval, can I really conclude that there's a change in your score based on where you sit? No. Now, if 0 was not included in that interval, so for example, let's say both of the numbers were negative, then I would say that that we are 95% confident that the decrease in score per row would be between 3 points and negative 0.8 points. I mean, all I can say here is that we're 95% confident that the change in score is from a loss of 3 points to a gain of 0.8 points. That's what the literal translation of that unit of that interval would be. So let's write that down so you know how to write it. And I'm just going to kind of round a decrease of 3 points to an increase of 0.8 points. So it really doesn't help us conclude whether or not there's a, to answer the question, like does proximity, does being further away from the front hurt your score? Well, all I know is that I'm 95% confident that the answer lies within that interval. So it doesn't really answer the question because 0 is included in it. So part E, we can take it one step further. Based on our interval, is there convincing evidence that seat location affects the scores? And here we would say since 0 is contained in the interval, we cannot conclude that there's a change in scores based on seating location. Or based on proximity. Okay, in example number 2, you are actually given the data and you have to go through the whole process of coming up with the confidence interval to estimate the slope in this particular example. So in this case, we've actually visited this example before where we're looking at customers at a buffet and seeing how if the length of time they're at the buffet affects the amount in tip they are given. So we're looking at the rate of change in the tip over the minutes spent at the buffet, and we're trying to estimate a confidence interval for that rate of change because that's what the slope represents. So in this case, you're given some data, you're asked to determine the regression equation, and then you're asked to do things like construct the scatter plot, do a residual plot, and verify that a linear model is appropriate. Check your conditions for inference. So take a few minutes to go through this problem. I'd like you actually to press pause and spend a few minutes working together to see how far you can get through this problem. And then towards the end, especially when it comes up to calculating the confidence interval, you can actually use, if you go on your calculator to your test menu, there's actually a confidence interval for slope. And if you scroll down to the bottom, you'll see there's a linear regression t-test and a linear regression t-interval. So when you're ready and you've checked all your conditions, try that command and see if you can figure it out for yourself. So at this point, I'd like you to press pause and then start the video back up after you all have had a chance to work through the problem. Okay, let's go ahead through the problem. I'm going to go through it kind of quickly because hopefully you've already done most of the prompts. So we're looking again at this data on the amount of time spent at a buffet and the amount of tip that was left. You're first asked to come up with the regression equation. So if you've done that correctly, I imagine you all probably did that correctly, you should end up with y hat is equal to 0.03x plus 4.535. You're asked to interpret the slope. So that 0.03 is basically saying as the length of time at the restaurant increases by 1 minute, then the amount of tip is expected to increase by about 3 cents on average per minute. And so remember to include your wiggle words. You want to make sure that you're representing an average rate of change. This is what we're expecting in the long run. So other things you need to do are checking the conditions. And this time there's 5 conditions. 2 of them we're used to, the independence condition or the random condition or 10% condition. These 2 conditions we have seen in every single test we've done. The other 3 are different plots. So you're essentially constructing 3 plots. You're going to do your regular scatter plot, which is right here. Your residual plot, which we reviewed in the warm-up, but I'll go through the process in just a second. And then you're also doing, this is new, the normal probability plot of your residuals. And so you need to make sure that all 3 of those graphs are included in your conditions and that you label each one, because they're just a bunch of dots. So you need to make sure that you reference which one is the scatter plot, which one is the residual plot, and which one is the normal probability plot. You also have to comment on what each of those things means. So the scatter plot, we're looking to make sure that our data is linear. I'm not going to bother performing linear regression and trying to estimate the slope of the line if the data I'm dealing with isn't linear. So that's the first condition that we're checking, and that's up here. So you're going to sketch the plot and then determine if it looks appropriate to perform linear regression. So not only are you going to show the plot, but you have to check the condition of linear enough. And so what I wrote in words is that the scatter plot shows a weak positive association between time in the restaurant and the amount of tip, and it is somewhat linear. The next thing you want to check is the residual plot. Is there equal variance of y? And this is sort of your confirmation that a linear model is appropriate. And so again, you're going to state which model it is. You're going to draw the picture, sketch it on your paper, state that it's the residual plot, and then indicate that the residual plot shows that there's an even scatter of points about the regression line, so a linear model is in fact appropriate. The last thing you want to check, this is our normal condition. Remember before when we were dealing with means, our normal condition just had to do with our sample size. And when we were dealing with proportions and counts, we were looking at expected counts of successes. Well, we have a different situation now. What we need to make sure is normal is our residuals. So let me go through how to construct each one of these plots. So you'll notice that I already have my data in my lists, in list 1 and list 2. To come up with the scatter plot, we hit second y equals. And then if I press enter, I just want to make sure it's all set up. The first graph is my scatter plot. I want to make sure my x's and y's are coming from the right place, and then I can hit zoom 9, and that gives me my scatter plot. For the residual plot and the normal probability plot, I must have the regression equation pasted in y equals. So I'm going to go to stat, calc, I choose linear regression, option 4, I tell the calculator where my data is, and then I have to make sure where it says store regression equation that I put the equation in y equals, because the calculator can't calculate the residuals or do a normal probability plot unless it has the equation stored in y equals. So I go to vars, y vars, it's a function, and it's a y. So I'm just going to store it in y1, and then I can go ahead to calculate. And so now if I go into y equals, I can see my equation there. If I go into the graph, along with my scatter plot, now you can see my regression equation. The residual plot is just another scatter plot. So again, I'm going to go into second y equals. I'm going to choose that first plot again. And what I'm plotting are my x values over my residuals. So if you scoot down to where it says list 2, and then hit second stat or second list, this gives you the names of all your lists. If you either scroll to the bottom of the list, if you scroll to the end of the list, or actually if you just scroll up, you'll see that the very last list says residuals. So choose that list and then do zoom 9 again, and this will give you your residual plot. And remember, the horizontal line is your regression equation. Every once in a while you'll see a line kind of flying through your graph, but your regression equation is going to be that horizontal line. And we don't want to see any patterns in the residual plot. We want to see that equal variance of points, that even scatter that's random around our line. It just lets us know that our line cuts through our data evenly. And then the last thing we want to check is that normal probability plot. This is the first time we have to change our plot. So I go into my plot menu again, and this time I'm changing from a scatter plot, which is the very first graph, to the normal probability plot, which is the last one. So I'm going to change to my normal probability plot. And then again, all my x's are in list 1. The calculator knows what to do. Hit zoom 9. And there's your normal probability plot. And that is really straight. That indicates then that our residuals, not our y values, but the residuals, so that even distance between my points and the regression line, it tells me that those are normally distributed. And that's my last condition. That's my normal condition when I'm doing inference for regression. So I've checked all my conditions. They've been met. I'm going to go ahead and perform a linear regression t-interval. And we can say for slope since we're essentially just doing the slope and not the y-intercept. And so this regression or this inference method, again, it's if you go to your stat and then your test menu, it's toward the bottom of the list, so sometimes it's faster just to scroll up. If you have an older calculator, you might not see the command for linear regression t-interval. The formulas are really, really complicated, and I would just suggest that you grab one of my calculators. You could absolutely check it out on the day of the exam, but if your calculator does not have the linear regression t-interval command on it, then you will definitely want to borrow one of my calculators. If we choose that command, it's pretty self-explanatory what you need to do. Our x's are in list 1, our y's are in list 2. We're going to indicate the confidence level, which in this case is a 95% confidence interval. And then notice it says the regression equation. Again, my regression equation has to be in y equals in order for my calculator to determine a confidence interval for the slope. And so I'm just going to go ahead and select vars, y vars, function y1, because that's where my equation is, and then I'm going to go ahead and calculate. Okay, and so you'll see your calculator will give you the slope. It gives you the estimate of slope is 0.03, which is what we knew. I can go ahead and state my confidence interval. So it's a 95% confidence interval for slope, and it goes from a negative 0.024 to a positive 0.085. And this is in dollars per minute. Remember, we're dealing with the slope. So I'm going to go ahead and just put my units, dollars per minute. Okay, and so you can see also the degrees of freedom. Since I'm dealing with a t distribution, I want to include the degrees of freedom. We had 12 customers or 12 receipts. So if you remember, the formula is 12 minus 2, which tells me my degrees of freedom is 2. You can see S is your standard error. You've got your R squared, your R. I don't think you need any of those other things. The A value that you see there, if you scroll down, that's your y-intercept. We're not really interested in the y-intercept at this point, but we do want to be able to interpret our confidence interval. Remember, with slope, we're interpreting, or we're trying to estimate the rate of change. So we're looking at the rate of change in tip for every minute that a customer spends in this restaurant. So I'm just going to say we are 95% confident that the rate of change in tip per minute is between a negative, I'm going to put this dollar sign, 0.02 cents and a positive 0.09 cents. Okay, and so let's think about what that means. The one thing you want to notice is that 0 is contained in the interval. And so if 0 is contained in the interval, if our slope is 0, that is basically saying that there is no change. There is no change in tip over time. And so because 0 is included in the interval, I really can't conclude any kind of significance with respect to the amount of tip over time. And so what we want to see usually if we're trying to estimate our slope is that either the entire interval is positive, which would indicate that our rate of change is positive and that the values are increasing, and then, or if the interval is negative, then we know we have a negative rate of change or a negative slope. But when 0 is contained in the interval, that is basically telling us that we don't have evidence that there is a change in the y values for increases in x, or in this case, we don't have any indication, or we can't prove that the tip is dependent on the amount of time, or is it's associated with the amount of time in the restaurant. Okay, so I know that was a mouthful. I know that's a lot. Most of the time when you see these types of problems, you will be given all of the output. In fact, most of the time, you will be given all 3 of the graphs and the computer output, and you simply just have to put all the pieces together and interpret them. I'm going to show you the whole process just because you need to know it, but I think most of the time on the AP exam, they hesitate from giving you a lot of data to have to input into your calculator because it's really easy to make a typo when you're entering this stuff in. So a lot of times with these problems, you're just given the output. We will go over this some more next class, and I will also talk to you about how to do a test of significance for slope. But in the meantime, just do the best you can. I will answer all your questions next class. I promise. I know this was a lot. Thank you for bearing with me. I will see you next week.